our next topic we're going to talk about is called stoichiometry. So I don't know what you've heard about it, but stoichiometry we're going to use pretty much the rest of the year. So the way to best think of stoichiometry is like a recipe. So you have all your ingredients, and then the amount of all the ingredients, and then if you notice down here, it tells me how many we're going to make. So 3 dozen in this case. So stoichiometry is predicting quantities in a chemical reaction. So if I go back to this example, you can see all your ingredients with the products that we're going to get. If I had 1 teaspoon of soda, I would be able to get 3 dozen cookies. If I had 2 teaspoons of soda, I could predict that I would be able to make 6 dozen cookies for every 1 or 2 teaspoons of soda. So here's what we're going to do. We're going to start with an equation, and all these boxes are supposed to be the yield sign, so I apologize. Every time you see a box, it's my yield sign. So we're going to start with an equation, and we do have to make sure that equation is balanced. So hopefully you notice that it's definitely not. We have a couple of coefficients we need to add. So we're going to put the 3 there. The N2 looks all right. We need to sneak in a 2 there. So now my equation is balanced. So equation's balanced. We're good to go. So once again, I want you to think of the chemical reaction like a recipe. All your ingredients, what you need. We're going to be looking at ratios. So if I look at my ingredient again, my example I told you, the 1 teaspoon for every 3 dozen. So that would be a ratio. We can do the same thing with our equations. We're going to have what's called mole ratios. So there, remember that's a yield sign there. So I can come up with several mole ratios based on this one equation. So I could have 1 mole of N2 for every 3 moles of H2. So like in a recipe, you're looking at all your ingredients. 2 moles of NH3, 1 mole of N2. Where are these numbers that I'm looking at? Where am I getting those numbers from? Hopefully you saw that I'm getting these numbers from the coefficients. So there's nothing in front of N2, so that's just a 1. Your mole ratios, they're going to be used as your conversion factors. So you are able to switch them, what goes on top, what goes on bottom, depending on what conversion you're going to be able need it for. So yeah, that's mole ratios. So types of problems that you will have that involve your mole ratios are going to be something like this. So I'm still sticking with that same equation that we balanced already. So the question is asking how many moles of N2. So here's what I want my answer to be in. And I want to make, or I'm starting with 2.3 moles of NH3. So how you're going to set this up is just like all of your other conversions. Take what's given, so the 2.3 moles of NH3. I'm already thinking, okay, I got 2 significant figures there, so my answer will be 2 significant figures. So take what's given, put it over 1. Now we're going to set up our conversion factor. So here's where my mole ratio comes into play. So I have moles of NH3 that I'm given. It's on top. So it has to go on the bottom here in my conversion factor. So that way I'm able to cancel it out. I'm trying to solve for moles of N2. So that one, moles of N2, will go on top. Now I told you before that every time you have mole, you're going to put a 1 with it in the conversion factor. That's only true when you're converting from moles to something else, such as grams, or moles to atoms, moles to molecules. When you are doing mole to mole, so your mole ratio, you do not automatically put a 1 with the mole. These numbers are going to come from the balanced equation. So we have N2, no coefficient, we get a 1. NH3 right there, we need a 2. So now my problem is all set. So you can see that the moles of NH3 will be canceled out. So we'll be left with moles of N2. So to do that calculation in your calculator, you're going to plug in 2.3 divided by 2. My answer that I'm going to get is 1.2 moles, and we're going to label it N2. So you can see why I stressed earlier why it's so important to always make sure you label what compound we have, because we just converted from NH3 to N2. So we're switching compounds here. Definitely want to keep track of which compounds you have. So stoichiometry is different from the other conversions, even though it's very similar. The reason why it has this whole special fancy name is because stoichiometry allows us to convert between chemicals. So we're switching what we go to. So we have to make sure we have a correctly balanced equation because you need those mole ratios. The mole ratios are what allow us to do that switch. So here's another example. We're doing the same thing. If you even want to pause this video, try to figure it out on your own and then check and see if you did it correctly. So we are looking for moles of H2. We have moles of O2. So again, we're going to start with what we've been given, making sure to label it, label what elements I have, put it over 1. Setting up the conversion factor, moles of O2, so moles of O2 automatically goes to the bottom there. We're trying to find moles of H2O, so we'll put that on top. We have to check now our balanced equation to put in the correct coefficients. So we have a 6 here, a 5 here. So we'll cancel out. We're left with moles of H2O. Perfect. So we're going to do 0.176 multiplied by 6, all divided by 5. So everything on top divided by everything on the bottom. We need 3 significant figures, because if you look back at the number that they gave us, 0.176, that is 3 significant figures. Remember that 0 in front doesn't count as a significant figure. So you label your answer. Voila, done. Okay, so we've been doing the 2-step conversion, so going from mole to mole. But what I want you to think about, what if you have grams of something and I want grams of something else? What kind of steps would we have to do then? We're going to put everything we've done so far in this unit all together. So we have our balancing equations. We're going to bring in the molar mass, gram to mole conversions. We just covered the mole ratios. So we're going to put it all together. So you know all of these steps. It's just putting it together. So I think this handout is very handy, this little graphic organizer chart, that if you want a copy, I can definitely give you one. Just make sure to ask me. I have copies. So the question I said earlier, what if I have grams of one thing and I want to find grams of another thing? So notice how I kind of color coded. The blue is one compound, the green is another compound. There is no direct connection between these two. So what I have to do, if here's my starting point, here's my ending point, we're going to go start here. We're going to do this conversion. We just learned how to go mole to mole, and then we're going to do this conversion. So 1, 2, 3, 4 steps that we have to do to get there. So let's see how that looks in a real problem. So again, here's my little yield sign. We do need to start with a balanced equation. So by a quick check, I see that that equation is not balanced. So hopefully you've already balanced it on your paper. I'll stick a 2 there. Feel free to pause anytime so you can kind of test yourself, see if you're getting it as I go through it. So let's see, this problem, starting with grams of fluoride, and we're looking for mass, which we measure in grams, of nitrogen trifluoride. So we're going to do just like I kind of pointed out right there. We've got 4 steps. Oops. So we're going to start with the 13.6 grams of fluoride. So if you look at how fluoride is written in the equation, we have F2. Definitely want to make sure you're using the F2, not just one F. That's going to throw off your calculations. So I've got what I'm given. So now I got to figure out where I go next. My next step is to go to moles of that F2. So to do that, we need to calculate molar mass using the periodic table. So let's go back to that. Grams of F2, since it was on top in the previous step, automatically goes on the bottom. My chart just told me I'm going to convert to moles of F2. So here's where, when you have moles, you can automatically put a 1. So converting between moles and grams, moles automatically get a 1. Looking up the mass of fluorine on the periodic table, it's 19. We have F2, so we need to make sure to multiply that. So that will give me grams of F2 that I can cross out. So I'm left with moles of F2. So we are right here at the moles of 1. I want to now switch to the moles of my second compound. So to do that, we're going to use the mole ratios. So moles of F2 up top automatically then has to go on the bottom. We're trying to find nitrogen trifluoride, so that's what's going to go on top. Nitrogen, 3 of the fluorines. So mole ratio, we're going to pull those numbers from the balanced equation. F2 is a 3. The NF3 gets a 2. So we can cross out our moles of F2. So we're up to moles of NF3. Our next step, our last step, is to get to grams of the NF3. So last conversion to set up, moles of NF3 will go on the bottom here. And we're converting to grams of NF3. Mole always gets a 1. Grams of NF3, when I pull those numbers from the periodic table, 71.01. Moles cancel out, so we're left with grams of NF3, which is what we're trying to solve. So perfect, we have all our steps set up. So I'm going to multiply everything on top, so 13.6 times 1 times 2 times 71.01, and I get, now I'm not going to round here yet. I'm not going to round to correct significant figures until I get to the very last step. Okay, so on top's good. Now we're going to do the bottom. 1 times 38 times 3 times 1, 114. Now this step that I just did, the top, and I have it set up so I can divide by what's on bottom. You don't have to show this step if you don't want to, just depending on your calculator. If you can do it all in one step, that's fine. I don't need to see that extra step there. So now we can do our top divided by our bottom. Final answer, 16.9 grams of NF3. So I have 3 significant figures, and I'm using 3 significant figures because the number that the problem gave me was in 3 significant figures. So this is the number that you're using to determine how many significant figures your answer should have. So I have one more example that I would like to work through with you. So again, this equation is not balanced. So this needs a 2. Need to stick in a 2 there. CL looks good. I need a 3 there. Okay, so now my equation is balanced. So we can see, here's what I have to start with. I'm looking for molecules of KClO3. Okay, so that's something new. Let me go back to my chart so I can kind of get a game plan in mind. So I am starting with grams, and I'm switching to molecules, which is up here in this corner, of an entirely different thing. So now you can see the path I gotta take to get that way. So still got 4 steps to do, but we're gonna follow and set up my conversions slightly different. So let's see, we're still starting with the 127.5 39.6 grams. And we have grams of potassium, so we'll put that in. Put it over 1. So my chart was telling me I'm going from grams to moles. So grams of K goes on the bottom. Moles of K goes up top. 1 automatically for my mole. Grams I'm going to get from the periodic table. 39.10. Cross, cross. So next step, we're up to moles of potassium. I need to go to moles number 2. So we're switching to KClO3. So moles of K on the bottom. Moles of KClO3 up top. So we're going to look up our molar ratio. Both of these have a 2. So we can cancel out moles of potassium. So, all right, so we're here. Next step is here. We're going to convert to my molecules. So my moles will go on the bottom. And molecules, I'm going to put on the side here because it doesn't really fit that well. KClO3. Moles automatically gets a 1. Hopefully you remember now. My molecules get to 6.02 times 10 to the 23rd. Cross those out so that we're left with molecules, which is perfect. That's what I'm trying to solve for. Now I do want to show you something else here too. 2 to 2 for my molar ratio. I'm going to cancel those out. That will save me a little bit of work. So now let's see. We can multiply everything on top. So we have the 127.6 times 6.02 times 10 to the 23rd. So when I do that calculation, 7.68152 times 10 to the 25th. I'm saving my rounding for the very end. And again, if you don't want to show this step, that's perfectly fine. Multiplying on the bottom, all I'm left with 39.10. So then my top divided by my bottom, 1.965. I need 4 significant figures because the number that they gave me in the problem also has 4 significant figures. And we have molecules. Make sure we label it. Make sure you tell me what chemical we're talking about. And we're done. So I know that was a long lesson, a lot of information to process. So I just wanted to leave you on a happier note with Amedeo Avogadro.